Welcome to the example of sequencing n jobs on 3 machines. The table given to us shows the processing times in hours of 7 jobs to be processed on 3 machines, M1, M2 and M3. And the order in which each of the jobs is to be processed on these 3 machines is M1, M2, M3. So basically every job has to be first processed on machine M1, then on M2 and then on M3. Sequence these jobs using Johnson's method and find the overall processing time. Find also the waiting times of the jobs and the idle times of the 3 machines. So basically we are being asked to sequence these 7 jobs on these machines so that the overall processing time is minimized. So basically there are these 3 machines. Suppose M1, M2 and M3. And there are 7 jobs which need to be processed on these 3 machines, which are A, B, C, D, E, F and G. Now each of these jobs is to be processed on machine M1 first, then on M2 and then on M3. For example, suppose we are scheduling job F first. So it has been given that F take 5 hours on machine M1, 6 hours on machine M2 and 14 hours on machine M3. So what this means is that first F has to be processed on machine M1, which will take 5 hours. Then it has to be processed on machine M2, which will take 6 hours. And then it has to be processed on machine M3, which will take 14 hours. So given this information, we are being asked to find out which job should be processed first and so on, so that the overall processing time can be minimized. Now let us understand how Johnson's method can be applied to sequence n jobs on 3 machines. Johnson's method can be applied in problems of sequencing n jobs on 3 machines only when certain conditions are fulfilled. These conditions are: first, minimum processing time on machine M1 is greater than or equal to the maximum processing time on machine M2. So minimum processing time on machine M1 is greater than or equal to maximum processing time on machine M2. And the second condition is that minimum processing time on machine M3 is greater than or equal to maximum processing time on machine M2. So minimum processing time on machine M3 is greater than or equal to the maximum processing time on machine M2. So if any one or both of these two conditions are satisfied, then Johnson's method can be applied. So this is either one or two or both. Now let us consider the example that has been given to us. So we have jobs, then M1, M2 and M3. So let us list the jobs and the times. A, B, C, D, E, F and G. 1, 3, 7, 9, 4, 5, 2, 7, 3, 8, 2, 8, 6, 1, 8, 10, 9, 11, 9, 14 and 12. So let us evaluate if Johnson's rule can be applied to solve this case. So the first rule says that the minimum processing time on machine M1, which is this, should be greater than or equal to the maximum processing time on machine M2, which is this. So let's see. The minimum processing time on machine M1 is 1. So the first rule is 1 is on M1, and the maximum processing time on machine M2 is 8. So on M2 the maximum time is 8. So is the first condition fulfilled, that is 1 greater than or equal to 8? No. So this condition is not satisfied. Now in order to follow the Johnson's rule, it is either 1 or 2 or both. So let's see if condition 2 can be satisfied. So the second condition says that the minimum processing time on machine M3, that is here, is greater than or equal to the maximum processing time on machine M2, that is this here. So let's see, the minimum processing time on machine M3 is 8. So M3 is 8, and the maximum processing time on machine M2, this is also 8. So M2 is 8, and 8 is equal to 8 on machine M1 and M2. So this condition is satisfied. So basically here we can use the Johnson's rule to schedule the jobs on these three machines. So just to make it easy to remember this rule, basically what this rule is saying, either the minimum on M1 is greater than or equal to maximum of M2, or the minimum processing time on M3 is greater than or equal to the maximum processing time on M2. So basically we are evaluating the minimums of the machines on the side to the machine on the center, that is the minimum of M1 and M3, either of the two, if it is greater than or equal to the maximum processing time on machine M2, then you can use Johnson's rule. Now once we have ascertained that we can use Johnson's rule to solve this problem, let's see how to solve this problem. So what this rule says is that convert these three machines into two machines, say a hypothetical machine X and a hypothetical machine Y. Now the processing time of various jobs on machine X is the sum of the processing time of the corresponding jobs on machines M1 and M2. So basically for each job the time on X should be the addition of the time between M1 and M2. Similarly, the processing time of various jobs on Y is the sum of the processing times of the corresponding jobs on machines M2 and M3. So for Y, we'll do the addition of the times taken by M2 and M3. So let's calculate X and Y for jobs A, B, C, D, E, F and G. So for A, for X, it is the addition of M1 and M2 for A. So 7 plus 1, this is 8. Y, addition of M2 and M3, so 7 plus 8, this is 15. B, for X, addition of M1 and M2, so 3 plus 3, 6. And B, for Y, addition of M2 and M3, which is 10 plus 3, that is 13. Similarly for C, 7 plus 8, that is 15. And Y, 8 plus 9, that is 17. For D, X is 11 and Y is 2 plus 11, 13. For E, X is 8 plus 4, 12 and Y is 8 plus 9, that is 17. For F, X will be 6 plus 5, that is 11 and Y will be 6 plus 14, that is 20. And for G, 2 plus 1, 3 and 1 plus 12, 13. So basically what we have done here is that we have converted the problem of sequencing n jobs on 3 machines into a problem of sequencing n jobs on 2 machines. And then let's look at how to solve this to get the overall minimized processing time. So let us first note down the jobs and the times taken by X and Y. So jobs and X and Y. B, C, D, E, F, G. 8, 6, 15, 11, 12, 11 and 3. For Y, 15, 30, 17, 13, 17, 20 and 13. Now let's first select the shortest processing time. So here the shortest processing time is for job G on machine X, that is 3. Now as per the Johnson's rule, if the shortest time is for the first machine, do the job first, and if it is for the second machine, then do the job last. So this is for the first machine, that is X, so we'll sequence G in the beginning. Let's cut this line because we have considered it. Next, the shortest time is 6, which is again on X, so we'll list B after G. We'll cut this line. Next, the shortest time is 8, so this is also on machine X, which is the first machine, so let's plot B and then A, so A is after B. Let's cut this line. Now the next shortest time is 11, which is for D as well as F. Oh, so we have a tie here. Both D and F have 11 as their processing time, and both of these are for machine X. So we can do either D first or F first. So what this means is that we have two sequences. So we started with G, B, A, and then we can have D first and then F, or we can have G, B, A and F first, and then we can have D. So let's now cut both D and F because we have processed them. The next shortest time is 12, which is on machine X and for E. So next we'll sequence E. Let's cut the line, and then we have only one job remaining, which is C. So C will be processed in the end. Now we have also been asked to find out the waiting times of the jobs and the idle times of the three machines. So let's do that. But first let's note down the original problem so that we can easily look at the data. So we have jobs M1, M2, M3, A, B, C, D, E, F and G. 1, 7, 8, 3, 3, 10, 7, 8, 9, 9 to 11, 4, 8, 9, 5, 6, 14 and 2, 1, 12. Now in order to calculate the waiting time of the jobs, let's list the jobs in any one of these sequences. Let's take the first sequence. So we'll have jobs, then for machine M1 we'll do in time and the out time. For machine M2 we'll do in, out, and for machine M3 in and out. So jobs will have G, B, A, D, F, E and C. So first job is job G. Now since we are starting from job G, it can come into M1 at 0th instance, and it has been given that it takes 2 hours to process on M1, so it will be out at the 2nd hour. Then on machine M2 it can be started at the 2nd hour, and it takes 1 hour to process on machine M2, so it will be out on the 3rd hour. On machine M3 we can start processing job G at the 3rd hour, and it takes 12 hours to complete on machine M3. So 3 plus 12, that is 15, so it will be out at the 15th hour. Now just to be clear on what is this out and in time for the 3rd hour, for example, you can consider this 3 as 030000, where 03 is hours, minutes and seconds, and then this 3 can be 030001, where again 03 is hours, 00 is minutes and 0.1 is seconds. Similarly, let's calculate the in and out times for all the jobs on the three machines. So B can be started on machine M1 at the second hour, and it's been given that B takes 3 hours on machine M1, so 2 plus 3 is 5. Now on M2, though M2 is finished processing G at the third hour, but since B is still being processed on M1, M2 has to be idle till M1 is finished processing B, and then job B can be processed on M2 starting the 5th hour. Now B takes 3 hours on machine M2, so 5 plus 3, 8. Now here, though B is already processed on machine M2 by the 8th hour, but M3 is still busy processing G. So we'll start processing B on M3 at the 15th hour. Now it has been given that B takes 10 hours on M3, so 15 plus 10, that is 25. Similarly for A, the in time on machine M1 is 5 and out time is 6. On M2, in time is 8 and out time is 15. On M3, in time is 25 and out time is 33. For D, it is 6, 15, 15, 17, 33, 44. For F, started the 15th hour, finished on 20th hour. For F on M2, start on the 20th hour and finish on the 26th hour. For M3, start on the 44th and finish on 58. Similarly for E, 20, 24, 26, 34, 58, 67, 24, 31, 34, 42, 67 and 76. Now based on this information, let's calculate the waiting times. Now for job G, it starts at the 0th instance, comes out on the 2nd instance, goes in at the 2nd instance, comes out at the 3rd, goes into M3 at the 3rd, and comes out at 15. So there is no waiting time, so waiting time for G is 0. For the second, that is job B, it comes out of machine M1 at the 5th hour, goes into M2 at the 5th hour, comes out at the 8th hour, goes into M3 at the 15th hour. So there is a waiting time here between M2 and M3, which is 15 minus 8, which is 7. For job A, it comes out of M1 at the 6th hour but goes into M2 at the 8th hour. So we have 2 hours waiting time here, and then it comes out of M2 at the 15th hour and goes into M3 at the 25th hour. So we have 10 hours here. So 10 plus 2 total is 12 hours waiting time. For D, 6, 15, 15, 17, and then there is a waiting time between M2 and M3, which is 33 minus 17. This is 3, 7, 13, 6, 2, 1, 2 minus 1 is 1, 16. So this is 16. For F, it goes into M1 at the 15th hour, comes out at 20th, immediately goes into M2 at the 20th hour, comes out at 26th. and then it has to wait till the 44th hour to go into M3. So the wait time is 44 minus 26. This is 14 minus 6 is 8. This cancel 3. 3 minus 2 is 1, 18. So wait time is 18. For E, it goes into M1 on the 20th hour, comes out of M1 on the 24th hour, goes into M2 on the 26th hour. Alright, so there is a waiting time of 2, which is 26 minus 24. So 2 hours between M1 and M2 for job E. Now it goes into M2 on the 26th hour and comes out on the 34th hour, and then goes into M3 on the 58th hour. So there is a waiting time of 58 minus 34, that is 8 minus 4 is 4, and 5 minus 3 is 2, so 24 hours. So overall for job E, the wait time is 24 plus 2, that is 26. Now similarly for C, it goes into M1 on the 24th hour, comes out on the 31st hour, goes into M2 on the 34th hour. So there is a wait time of 34 minus 31, which is 3 hours on job C. Now it comes out of M2 on the 42nd hour and goes into M3 on the 67th hour. So there is a wait time of 67 minus 42, 7 minus 2 is 5, 6 minus 4 is 2, so 25. So overall there is a wait time of 25 plus 3, that is 28 for job C. So this is 28. So we found the waiting times of each of the jobs. Now the overall processing time to finish all these jobs on these 3 machines is 76 hours. Now we have also been asked to find out the idle times of the 3 machines. So let's now try and calculate the idle times. Let's first do M1. Now let's see if M1 has any idle time starting from the 0th hour going to the 76th hour. So 0, 2, 2, and then again it starts B on the 2nd hour, finishes 5, 5, and then again starts A on the 5th hour, 6, 6, 15, 15, 20, 20, 24, 24, and then 31. Now after 31, it is idle till 76th hour. So M1 is idle for 76 minus 31, which is equal to 6 minus 1, 5, 7 minus 3, 4. So 45 hours. Let's do machine M2. Now machine M2 starts processing jobs at the 2nd hour. So this has an idle time of 2 minus 0. And then let's see if we have anything more. So G gets processed on the 3rd hour, and then it processes B on the 5th hour. So we have an idle time of 5 minus 3. Let's see if we have more. Then B gets processed on the 8th hour. Then again it takes A on the 8th hour, processes it till 15, takes D on the 15th hour, processes till 17, and then it processes F on the 20th hour. So there is a wait time or idle time of 20 minus 17 here, plus then it processes F till 26th hour, starts processing E on the 26th hour, finishes 34, 34, and then finishes 42. So after 42, then again it has a wait time or an idle time till all the jobs are completed on machine M3, which is 76. So plus 76 minus 42, This is equal to 2 plus 2 plus 3 plus 6 minus 2, 4, 7 minus 4, 3. This is equal to 34, 35, 36, 37, 38, 39, 40, 41. So 41 hours. Let's calculate same way for machine M3. So machine M3 has an initial idle time of 3 hours because it starts processing G on the third instance, so it has 3 minus 0. Let's see if it has more idle time. So it comes out on the 15th hour, goes to process B again for the 15th hour and finishes 25. A again goes in at 25th, 33, 33, 44, 44, 58, 58, 67, 67 till 76. So there's no other idle time for machine M3, so this is equal to 3 hours. So machine M1 is idle for 45 hours, machine M2 is idle for 41 hours, and M3 is idle for 3 hours.